Hi, this is the first video of a video series on magnetic induction. So magnetic induction is essentially an overarching name for creating currents, like electrical currents, using either motion through a magnetic field or using changing magnetic fields to change over time. And magnetic induction is really the kind of area where we really get to understand how magnetic forces and electrostatic forces are linked and really have to be considered together, forming one theory of electromagnetism, one framework of electromagnetism that sort of encompasses all those effects. Understanding induction is also fairly crucial to understand a number of very important aspects of modern life, such as generators. Without magnetic induction, never mind that the universe wouldn't work the way it does anyway, but without magnetic induction, for example, we would not have power stations. There would be, you just wouldn't have an electricity network. And also a number of circuits in electronics. They use something called inductors that play very special roles in circuits that use induction and allow for things like tuning a radio or communicating via mobile phones at a particular frequency of electromagnetic waves. Of course, the whole notion of electromagnetic waves, among them light, is something we're going to come to after we've really understood the basics of magnetic induction. So magnetic induction, it is hugely important. It seems a bit more advanced of a topic than what we've done so far, but really, in a sense, it is very fundamental. So in this first part, I want to consider situations where we are moving a conductor through a magnetic field. And doing so creates an EMF, so a potential difference. Remember, EMF is just a fancy name for the type of potential difference created by, say, a battery. EMF stands for electromotive force, which is a very silly name because it is not a force, it's a potential difference. But it's, a historical term. We call this type of EMF, this type of potential difference, it gets created by having a conductor move through a magnetic field. We call it motional EMF because it's created via motion. The one situation that you might already recognize here is one that you met in the video series I made on magnetism. And the situation is that there's a bar, imagine maybe a metal bar, it's moving with some velocity v through a magnetic field. The magnetic field in this case I imagine to be straight down. A little crosses means straight down, but of course, it could be straight up, same thing. So what happens? If this is a conductor, right, then by going through here, through this magnetic field, I have particles, charged particles moving through a field, and that causes a force on those. So if you were a little plus particle sitting here, what would happen to you? Well, velocity is this way, the field is down, so by the right-hand rule, the force is going to be in this direction here. If you're a little minus particle, I apply the same right-hand rule, but it's a minus, so a little negative particle, it'd be pushed down. And so what this would cause is essentially that this conductor would just get polarized. Right, the minuses, some of the minuses travel down there, some of the pluses travel up there. Now, once the conductor is a little bit polarized, we're going to have an electric field inside it that points from the pluses to the minuses, and this is essentially going to balance out the force on other charges. So once we've got pluses up here, minuses down here, there's an electric field downwards inside this bar. So no further plus charges are going to move up, because yes, they get pushed up by the magnetic force due to the motion this way, but they're going to get cancelled out by an electric field pointing down. And if the electric field isn't strong enough, well, then more charges are going to migrate. That'll make the electric field stronger. So you find that once this has happened, we get the electric field inside the bar is going to be equal to the speed times v. How do I know that? Well, the electric field is Q times E. It's going to be electric force, the charge that's in here, times the electric field inside it, due to all the other charges having rearranged. Q times E is QVB. QVB is for the magnetic force, and then the Q and the Q, they cancel out. So this is how we get to this relationship. And if I have an electric field that's essentially the strength, it's constant, right, inside this bar, that means I'm going to get a potential difference that you might pick up by, say, hooking a voltmeter up between those two rails that I imagine this bar is traveling on. If they're also conductive, would hook up a voltmeter like this, get a potential difference that's going to be E times L, or in other words, V times B times L. So I talked about this already in the other video, and make sure you can follow along. Right? You need to have a good grasp of the basics of magnetism in order to make sense of induction. So if you're still feeling a bit shaky, you probably want to go back to some of the other videos that I made on magnetism. Alright, so the potential difference here is this. So what we can do now, of course, is we can so this applies, right? If you just rearrange, this would be essentially the Hall effect, as it's called, if you want to look this up. Now what we're going to do instead is we're going to hook those up, right? Not with a voltmeter, that there's no current going through it because it has infinite resistance. If you imagine doing something like this, maybe I have just a resistor here, a resistor R, and then I'm gonna get a current. Right? So if you hook those two up, you're gonna get a current. Positives go this way. So if hooked up, as shown, right, with the resistor, via a resistor connecting the rails, then we get a current. The current I, what's equal to, it's delta V over R. R is just what resistor I put there, which comes to be, you know what delta V is, the speed times the magnetic field times the length of this. So I get V times L over R. Let's make sure we don't get confused between the delta V, meaning the potential difference, and the little v, meaning the speed. And v for velocity, of course, but here we know which direction it is, so this is really just the speed here. So let's analyze this expression, though, in a bit more detail. I want to take this one here. Delta v is the speed times the magnetic field times the length. I want to figure out how to interpret this. So let's look at delta V, the potential difference. That's my induced EMF, right? We say this, a bit of terminology here. This current that we're getting, this current is induced. It's an induced current, magnetically induced. It's just terminology. Okay, let's look at this expression here. Delta V is V times E times L. So what is this? Specifically, I want to ask, what is V times L? So let me write this again. Let me just rearrange it. V times V times L. What is this? If I multiply the speed by the length of this bar, the separation between the two rails. Well, if I imagine the speed is 2 meters per second, then I multiply 2, like the distance that this bar travels in 1 second, by the length like this. So if the bar goes to here after 1 second, right, and then this would be the speed. This length would correspond to the speed v times 1 second. So if I multiply this distance that the bar travels in 1 second by the length of it, I'm going to get the area that the bar sweeps out, right? So imagine this bar like leaves behind a sort of trail of color. Well, then this whole area will be colored in the 1 second. So V times L is the area swept out per second. Another way I could sort of characterize this is by saying it's the area that by which the area of the circuit increases. I could imagine I take the inside of this circuit, this loop, to be an area, and this area increases by an amount every second. It's V times L. So this motivates me to make the following definition. And the thing we're defining is magnetic flux. Magnetic flux works exactly like electric flux, from electric field lines and electric fields and so on. Magnetic flux, we call this phi B. It's phi for flux. Same thing with phi E for the electric flux. B because it's the B field, the magnetic field. I want to say this is going to be B dot A. So the area is once again defined the same way an area vector was defined in the case of electric flux, right? We imagine we've got an area here, trying to do it in 3D. I stick a little flag out 90 degrees, and this is the direction of A. Right. So in this case, we had here, you can imagine the area is flat on the sheet and the flag sticks like out towards the top or the bottom. The direction would just be a sign, changes it upwards or downwards. But it sticks out, it's like vertical. The flag is vertical. It's in the same direction as the B field, which is also vertical, pointing straight down. Magnetic flux is phi dot, B dot A. Right, the dot product, also write this as B, the magnitude of B, times the area, times the cosine of the angle between B and A. Again, that should be familiar from having done exactly the same thing with electric flux in the past. So what is this? What is the meaning of this? It's sort of like I'm looking at a certain area here, this area patch here, and I'm asking how many magnetic field lines are sticking through it. And if those field lines are all at a funny angle, sort of coming in diagonally in some way, then if the magnetic field was equally strong as before, just at a different angle, then you could easily check that fewer lines would stick through it. Right, so you might want to compare this situation here. This would be one situation. Here, theta BA would be 90 degrees. Sorry, it would be 0. So this is wrong. 0 degrees, because my flag sticks out this way, right? This is my flag. Same direction. There's 0 angle between the flag and the B field. Whereas in a case like this, I do it like this. When try to those field lines equally far apart, like this spacing is the same as this spacing here. it's just impossible to have the same number of field lines go through the area, even if the area is the same size because of the angle. And then if this is my flag, right, this would be my theta dA. And so if the magnetic field were perfectly horizontal, the same direction, I get an angle of 90, like the magnetic field points this way, the cosine of 90 is 0, so there would be 0 flux if the field points this way. Right, so again, if you're struggling with this concept, go back to what you learned about electric flux, because it's exactly the same. And of course, when I write the B and A without the arrow, I just mean the magnitudes. I could be writing, with an arrow an absolute value, but it becomes notationally cumbersome. So I'm just going to use the convention that if I don't write the arrow, I just mean the magnitude of the quantities. So having done this, I can just double check what's the potential I get here. So this is V times L was not the area, like inside the loop or something, but it was the change of area per time. Right? Was the crucial insight. So per second, this is by how much my area changes. So let me write this down here. Or change of area per time. Right. So I'm going to write down then my claim. And it's something we'd have to experimentally verify. Put on Faraday's law, as it's called. Faraday's law states that the induced EMF, delta V, we write delta V induced, or I could write it like this, right? Same thing. Is equal to the rate of change of magnetic flux. So this is a derivative. So how does this change with time? Right, that's, in a way, right now, this is our hypothesis. We've generalized a little bit, right? We said, look, we notice in the case, this example here, the bar sweeps out a certain area. Hey, the induced potential we get just from understanding forces on charges. That is equal to B times the change of area. So really, the delta V as a whole, the induced EMF, is just the rate of change of flux. Okay. So phi, right? The magnetic flux is equal to B A cosine theta. We sort of hypothesize a little bit. Before I actually go there, let me make one more statement. Really, what I mean, of course, by this is this is a statement in terms of absolute values. Right? The potential difference we're going to get is the absolute value of this. You sometimes see it written with a minus sign. It's to do with what's direction, but I think the minus sign is just confusing. It doesn't really help us understand what's going on. To figure out the direction of the induced current and the induced potential difference, we're going to use another law called Lenz's law that we're going to come to later. It kind of lets you decide, is it clockwise or counterclockwise? It's always a 50-50 with that. So really we use Faraday's law to establish how many volts is it. We're going to worry about the direction in some circuit later. Okay, so this is only a hypothesis in the sense that, yes, we've shown it for this one particular example where A was changing. But if this is true, that the flux could change in other ways. B could change. The magnetic field could become stronger or weaker. Or maybe the direction, the angle between A and B could change. For example, if my wire was in some way sort of rotating or the magnetic field was rotating. So, so we can get an induced potential difference via essentially three ways. Via one, or more of 3 ways. So we could have more than one change, right? So the area could change. A could change. It would be the area of my loop, my circuit, right? This closed conducting circuit, this loop. It could change the area by just moving the bar further right. Area of let me call it current loop. If you've been paying attention, you notice that this sort of plays into the whole Kirchhoff rule, right? It makes you doubt, wait a minute, is that stuff that I learned with Kirchhoff's rule about potential differences around loops, does that still apply? Well, you're going to have to modify this, right? If there are changing magnetic fields, say, or changing magnetic flux. So A could change, right? That was option 1. B could change. So e.g. the magnetic field, the B field, gets stronger or weaker. Right. And then A could change, B could change, C could change. No, not C, but the angle could change. For example, the wire might be rotating. And the prime example of that is most generators are built that way. So can I write EG and EG again? Is that allowed grammatically? I don't know. EG generator, like an example. This is an example. For example, the wire could be rotating. For example, a generator. Feeling grammatically insecure here about this construction. It's probably bad form, but who cares? I'm doing it. All right. So we're going to look at all of those cases. Of course, you could have a situation where more than one changes, right? We could imagine there's this bar moving, but also somebody is cranking up the dial that controls the strength of the magnetic field at the same time. Or somebody's changing the orientation of the magnets that create this magnetic field, or something like that. Right? That just makes it more complicated, doesn't change the underlying ideas. Okay. So, for the rest of this video, I really want to just look at other examples where the area could change, and we're going to look at the other cases down the road in the follow-up videos. So let's look at another example. Here's the example. I imagine there's a bar, again conducting bar, shown right here, and it's rotating inside a magnetic field. So maybe there's some kind of pin here, and then this bar itself might be conducting too, and I could imagine maybe I hook up, I have a cable that starts here, it goes down underneath the table, and maybe hooks up to the bar here. So imagine sort of like this. Imagine this goes underneath, just like this. There's some resistor here, and then it hooks up to this rail. So this makes sense to you, right? Or I could just say this thing is rotating without any cables attached, and then we're going to get a potential difference between out here and in here. So how fast is it rotating? That's going to be important, of course. It's going to be rotating with an angular velocity, a rotational velocity called omega. This is often the symbol used. You might have met this a little bit in your mechanics course, depending on how much time you spend on rotational mechanics. Probably not very much, but maybe you've met it. If not, it's a really simple idea. It's kind of like velocity in meters per second. Well, we're calculating something that is changing its angle over time, not its position left, right, up, down, right? So we're going to describe the rate of rotation in well, what angle gets swept out per second. And we're going to express this in radians per second, because that's mathematically more convenient in various ways. Right, so omega might be 2 radians per second, which would tell me that this thing is rotating 2 radians every second. Or maybe it's 0.1 radians per second, and then it'll be rotating 0.1 radians every second. So I hope this idea is clear. You can easily relate this quantity to, say, the total time around, or the number of times it goes around per second. So think about how to relate those if you haven't done that before. It doesn't require you to have any special knowledge, just to understand the concepts that I just mentioned. Okay. So we're going to assume this thing is rotating with angular velocity omega, maybe 2 radians per second. So what area of magnetic field, what magnetic flux gets swept out? So we're trying to calculate. We're going to find the potential difference between this point here and the rail out here. Right? Maybe I'll put it like this. I'm going to imagine I have my voltmeter here. I'm going to sort of hook one end here, hook one end there onto the rail. What am I going to get? Well, let's use Faraday's law. So Faraday's law stated that the EMF, let me use this one, the symbol this time, just to mix it up. And the EMF, the induced potential difference, the strength of it is the rate of change of flux. So in this case, it's the flux that this thing sweeps out every second. I guess I should put opposite value here. Okay, so what is this? Well, the magnetic field doesn't change, right? And the angle between the magnetic field points straight up out of the page, what the little dots mean, is in the same direction as the area. Because the area, if I imagine this area here, I'm looking down on it, the little flag that I might put on the area to show the direction of it, the orientation, would be sticking straight up. Right? Straight up. Same thing as the field. So the cosine of the angle, cosine theta AB is equal to 1. And the magnetic field is constant. So I am going to get B times dA dt, the rate between the area. Okay, what area is it? Well, if you imagine this is my voltmeter here, then of course this changes the area by a certain amount. It doesn't matter if it increases or decreases the area, it doesn't matter how I hook it up, but moving from here to here, the area is changed by essentially the size of that pizza slice. That is the initial and final position of the bar make over the course of that 1 second. So what is the area of the pizza slice? For the area of the slice, that is my dA dt, because this is the area, this is the change per second. It's going to be B times okay, so now I have to think about this. The easiest way to figure out what the area is of this is to ask, well, what fraction of the total is it? So all the way around, it's 2 pi. So I'm going to take omega over 2 pi. That is the fraction of the circle that's swept out. I'm going to multiply by the area of the circuit. So let me annotate this a little bit. So it makes sense to you. This thing here is the fraction of full circle swept out per second, because omega is defined as, an angle per second, and this one here is the area of the full circle. So multiplying those just gives me the area that's being swept out, the area of my little pizza slice. And now we're pretty much done. I can simplify this a little bit. The pi cancels out, and I'm going to get the final answer for my EMF. It's the strength of the magnetic field times omega times r squared. And you can't forget about the factor of a half. I guess I'm going to put it out front. A half b omega r squared. Right, that is going to be my induced potential difference. What current do I get? Well, that depends on the resistor you hook it up to. Maybe you use this potential difference for something else. Maybe you can charge a capacitor that way. Be a fun little another problem. Imagine I hook this up to a capacitor, right? And I charge a capacitor by doing this. And then I stop. And the capacitor we want to discharge. This creates a current, right? Through this. Imagine that this is not a resistor but a capacitor. I charge the capacitor by moving this bar. Then I make the bar stop. Then what's going to happen? Well, the capacitor wants to discharge just through this circuit. It creates a current in the bar, current in the magnetic field. We're going to get a force. The bar will start moving. Fun little problem to work through. Just see if we can make sense of that. Right? I'm not going to give you a specific question here. Just use your understanding of physics to figure out what would happen if this is a capacitor. I'm going to move it until the capacitor is charged. Then I stop. What will happen next? Fun little problem to think about. But for our purposes right now, we figured out EMF here using Faraday's law. Okay. I want to do one more problem. That's sort of related. One where we have actually to worry a little bit about the angle. So, another example. What I imagine now is I kind of have the same setup with the rails, except I'm going to have my rails go down a hill. This is my side view. I'm going to imagine this is my bar. The magnetic field points straight up. Straight up, of course. Right, magnetic field points straight up. This hill makes an angle, it's called alpha, with the hill. So this is the side view. The top view, if you like, would look something like this. Let me draw a top view of this. I just see the two rails from above, and I see this bar across it moving, and it's going to start moving down, of course. So from above, I would see the magnetic field come towards me. It will look something like this. So make sure you can visualize what's going on here. And let's suppose right now, the moment we are looking at this, the velocity down the hill is v. Right? This is the velocity in the downhill direction. So let's figure out what is the induced EMF between the two ends of the rod. I can't show you here. Here's like one is in front, one is kind of in the back, but here I can show you in the top view between here and here. What is the induced EMF? Induced EMF, let's call it curly E, is d phi dt. Okay, the magnetic field isn't changing. The angle isn't changing, but the angle is not. The angle is not like 90 degrees, or in other words, it's not 0 between the flag. Right, here's my little flag sticking out 90 degrees. That angle between the flag, that's this direction of the area vector, and the B field is not 0. Right, it's something. In fact, you can easily check that this angle here is also alpha. The easiest way to check this, if you don't believe me, like how do I figure this out? Sure, you could draw some triangles, or you could say, well, look, if this is flat like this, then there's 0. If I change this, like start tilting it like this, then I've tilted the vertical by the same angle, right? So like this. Maybe that'll help you just immediately see that this angle has to be the same as this one here. So d phi dt. So I'm gonna have what's changing. So this is, let me write out explicitly, d dt of the flux. The flux is the area times b times the cosine of alpha in this case, because that's the angle between the B field and the area. So those two stay the same in this example. So I'm going to have dA dt times B cosine alpha, and you can easily check that the area that this bar sweeps out is of course how far does it move per second times its length. Let's call it, you should give this length a name, by the way. It's going to be important, L. Alright, it's called L. So I get V times L times B times the cosine of alpha. It's kind of the same as before in our very first example, except we've got this new factor here that's going to like reduce the EMF, right? In the case where it was flat rails, alpha was just 0, and that makes the cosine of the angle as big as it can be, namely 1. So here the result is the same as before with the two rails, except that there's extra factor cosine of alpha. Another way you could have thought about this is essentially you say, I'm just going to worry about the component of the velocity that's perpendicular to the magnetic field. Right? So you look at it from above and you look at the component of velocity that's perpendicular, it's V cosine alpha. And that way you would have gotten the alpha as well, the cosine alpha the same way, right? So it's almost like when you calculate the flux swept out, you only worry about the motion in the direction that's perpendicular to the B field. It's another way to think about mathematically equivalent to what we've been doing. Right, so here's our answer. Now let's actually follow this problem up a little bit and just do a little bit of fun calculation here, and ask what is the terminal velocity of this rod. Okay, this brings us back to the idea of magnetic braking. Remember, once this rod starts moving, there's going to be a current in the rod. If you pretend now, we assume we're going to hook this up through a resistor of resistance R. Right? So for our calculation so far, we didn't say V stayed constant. We just said any one instant, the potential difference you get is the velocity you have right then times those other quantities. But now let's ask, how does this change over time? Something going down a hill gets accelerated by the gravity, namely the component of the weight in the downhill direction, right? It's basic mechanics. You've learned that when you learned about forces. The acceleration down the hill is g sine theta, where g is of course 9.8 meters per second squared if you're on Earth. But once there's a current flowing, there's going to be a braking force. Right? So let's put those pieces together. So you want to find the terminal velocity of the bar. Right, so it has terminal velocity where it will no longer accelerate even though it will be going down a hill, exactly because there's a braking force. i.e. when magnetic braking force is equal to mg sine theta, right? Where m is of course the mass of the bar. write this here, mass m. Now, I'm not going to go through all the detail here about using the right-hand rule to figure out, yes, there must indeed be a braking force. But remember, the logic was, okay, the bar moving as a whole creates a current in the bar. A current means charges are moving sideways because they're flowing inside the bar. That in turn causes a magnetic force on them that's backwards. Right, so there was a different example in a different video in the magnetism series. So check that out if you're confused about what I'm talking about here. So the braking force, so this is of course the weight component down the hill, right? I assume you understand this part. The magnetic braking force, what's this equal to, is I, the current, times L times B, right? Because this is a current inside a wire of length L going through a magnetic field, and of course the current, because the current goes like this, right? This is perpendicular to the magnetic field, so there's no extra angle dependence here. Again, make sure you understand that. That better be equal to mg sine theta when those forces balance out. And the current itself is, but I is delta V over R. Or maybe in this case I should not call it delta V, I should call it the induced EMF over R, because that's the potential difference, right? The resistor we're hooking up, that's what limits the current. If it wasn't there, it was a perfectly superconducting wire here, you just get a sort of infinite current going around, which means the bar wouldn't be able to move at all. It's an extreme case of magnetic braking, which indeed you get with superconductors. There's a really cool superconducting in effect, where essentially magnets sort of float above a conductor, based on principles similar to this. So check out some of superconducting, like magnetic braking with superconductors. Just search for that online. You find some really cool videos, stuff that you might be able to do in the classroom with the right setup. But it's a bit of a, it can be a bit of a hassle to set up. So just check out the videos. So let's come back to this. I is this, right? So, and we know what this is. This is VLB cosine alpha. So I've got V, the speed, and this is speed when those two are equal. B, L, cosine alpha over R. This was just I, now times L and B again, right? That is equal to mg sine theta. Okay, again, if you're lost right now, take a step back, make sure you understand magnetic braking forces from the previous video. This is the force. How do we know I? Well, it's potential difference over resistance. How do we know the potential difference? That's what's induced by the motion of the bar. So we can rearrange this to find a terminal velocity, and you just do this. You find V. Terminal velocity means we're no longer accelerating, that is why I can set the magnetic braking force equal to the downhill component of the weight, right? Because I'm assuming, I'm looking at the state where the rod is just rolling down the hill without speeding up. So the forces must balance out. Net force must be zero. That is why I'm setting those two equal. So I do the rearranging here, and what am I getting? I'm getting mg r from here divided by b squared, bb, and l squared. That's interesting, isn't it? Depends on those quantities twice. Sine over cosine, that's tan. Oops, of course I used theta here, I should have used alpha. Excuse me. point I wish I had a better eraser. Alpha, alpha. But of course it's alpha, of course, because that is the what we call the angle. All right, and that is our final answer. Now, if say you're starting just out, you're letting the thing go, and doesn't have any velocity yet. Well, in this case, it's going to just speed up. There's no magnetic braking force, no induced EMF. We're just going to have it speed up. As it speeds up, its speed increases. So you're going to get an EMF that keeps getting bigger because this thing here gets bigger as the bar rolls down the hill. But as this thing gets bigger, the magnetic braking force gets bigger because it depends on the speed. So the acceleration gets slower, and so it's still speeding up, but not as much. It keeps getting faster and faster and faster until magnetic braking force is so big that it equals mg sine alpha. Now, if you want to be super fancy here, you can take this yet one step further and actually calculate what is the speed as a function of time. It requires you to set up a small differential equation, namely, essentially f net equals ma, and f net depends on the speed, and a is the rate of change of speed. So see if you can set this up, especially if you've done any kind of differential equations course before. This is a fun little example to do for first order differential equation to solve. Find out what is v as a function of time, assuming you let the rod just start from rest up here. What you should find is that it sort of asymptotically approaches the terminal velocity, but never actually quite gets it. It goes like 99% of terminal velocity, 99.999% of terminal velocity, and so on. Anyway, so this is a little follow-up example and a follow-up calculation from this particular example. The most important part I want you to take away from this is how to compute the EMF. Alright, so this was part 1. In the follow-up videos, I'm going to consider cases where the magnetic field changes.